Joining us for a second interview is Drew Welton. It is likely that if you work on transformers or rent electrical test equipment that you are familiar with Drew. In addition to his role as VP of Sales for IntelliRent, he is also a 25-year senior member of IEEE who sits on various committees, including the Transformers Committee and the Power System Relaying Committee Working Group. Drew is always on the go, attending various conferences and providing training. Today, Drew is fresh off of training and coming to us live from the OMICRON Academy Training Center in Houston. Drew, welcome back, my friend. Last time, we mainly talked about insulation failures and transformers, mostly to do with moisture and the damaging effects, which was well received, and we've actually garnered over 7,000 views. It is our pleasure to have you join us again today, my friend. And as I understand, today's topic is on mechanical failures, correct?
Correct, Micah, and thanks. Certainly glad to be back with you, and thank you so much for this opportunity. And we're really delighted to do this presentation from a wonderful place here in Houston, Texas. A little bit warm outside, but being from Florida, definitely used to that. But we have beautiful blue skies anyway. So, you're right. Last time we talked about insulation failures, and that's one of the three categories of transformer failures. We have electrical, insulation failures, and then, of course, mechanical failures. Well, in terms of a definition, a mechanical failure basically involves the physical displacement or damage of parts within the transformer itself. And this can happen for several reasons. And I think probably most people are familiar with the physical damage that can happen to a transformer when it gets transported. Transporting a transformer can be a very difficult process, of course, because they're so large. It's either going to be on a flatbed trailer from the manufacturer to wherever it's going to end up. But in some cases, they put them on rail cars. Now, a rail car is really, when you get into the very large transformers, the only way to transport to a customer. And the problem with rail cars is, as it's going, across the country or however far it's got to go, they couple and decouple cars that are, on the rail system itself. And to use a term that might bring a few chuckles, it's called humping. When they connect.
You get one out of me, my friend.
Well, the problem is it causes a lot of shock and vibration. And can actually damage the windings of the transformer. So in order to try and get an indication if it's had too much damage at all, they put vibration monitors on the outside of the transformer, and they can record whether or not it's had excessive vibrations. But one of the things that the industry is more familiar with that deal with buying new transformers and looking for physical displacement is something we're going to talk about, and that is sweep frequency response analysis, or SFRA. But aside from transportation, you can also have physical damage due to seismic activity. Earthquakes can damage a transformer's internal components. On a generator step up, it could be from improper synchronizing of the generator that causes a large mechanical stress if you synchronize that to the line out of sync. But the one we're going to focus on today is called through faults.
Very cool. Now, with mechanical failures, can you offer a definition, like what defines a mechanical failure?
Sure. Well, that is, the mechanical failures is the physical displacement or damage of parts within the transformer itself.
Gotcha. Now, what are some of the causes of mechanical failure? Because I know we mentioned the vibrations and in transit and things like that. But they come to my mind, and physically moving the transformer from one location, kind of like we talked about. Are there any other expansive thoughts on that?
Sure. Well, transportation and movement, if you have a mobile sub and you're dragging that transformer over a dirt road with potholes, you have to be very careful that you don't damage. But one of the really major causes of physical damage in a transformer is what we call a through fault. Now, what's a through fault? Well, out in the power system, we have faults that are external to the transformer. In other words, if you study transformer protection, protective relays, you have a series of different types of protection. You have what we call current differential. Okay, when you have a fault inside the transformer itself, in a normal situation, the current of the current flowing through the transformer is equal to what goes in and comes out. That's the law of physics and
Yeah.
electronics. So if you have a fault within the transformer windings itself, that current doesn't escape, it tracks towards the fault, and what comes into the relay isn't equal to what's going out in terms of current. So we have a protective relay called a current differential relay that will protect the transformer from catastrophic failure if you have a turn-to-turn fault or some type of a fault within the transformer itself. There's other, but that is what I call a reactive protective element, not proactive, but reactive, because if the differential relay trips, that means the damage in the transformer has already occurred. Now, there are other protective elements for the transformer that keep outside influences from damaging the transformer. Things like a volts per hertz condition on a GSU, or overcurrent protection, or ground differentials or grounding errors in the transformer that may damage the transformer if we keep it online and that condition remains. So if in a through fault condition, okay, you have a fault that is outside that differential protection zone, either downstream or upstream through the transformer. Now, when you have a fault, say in a distribution circuit or out on a transmission line, the transformer will not take itself offline specifically because it's not seeing enough fault, but that through fault produces a physical force in the transformer itself that could either, if you have a high enough through fault with a long enough duration, could cause a buckling or some kind of a problem in the windings physically. So, how do we know when we've had through faults? Well, one of the things that is very important in terms of transformer protective relay systems is to have what we call a through fault monitor. And that is a monitoring system in the protective relay itself that measures both the duration of the through fault, how long it remains out there, the intensity of the through fault, how high it is, and then how many occurrences this has happened. Because physical damage in the windings of a transformer from a through fault may not happen just from one occurrence. It may be historically a number of occurrences that happen over time that causes the windings to start to weaken, and the physical components, the spacers, the barriers, everything that makes up the physical part of the windings of the transformer can be damaged.
Sure. No, that totally makes sense. And then kind of expanding on the throughput aspects of it. So I understand there's a monitoring. Would you consider that part to be the proactive part, or will the
Oh,
protective side of it kick that
absolutely.
off?
Yeah, and let's talk about that just briefly, because most all of your modern transformer protective relay systems have a through fault monitor. Now, I talked about this at a NETA conference about 2 years ago, and there was a good friend of mine from Schweitzer Engineering. He's gone into consulting at this point, but he was with Schweitzer for many, many years. His name is Carl Zimmerman, and Carl was a real colorful guy, just a very, very smart protection engineer, and he always focused on transformer protection for the most part. And when I started talking about the through fault monitor and relay systems, and Carl said, "Yeah, all our Schweitzer relays have a through fault monitor." He said, "But the problem I always saw in the industry is nobody ever enabled them." And that could
Is there
be,
kind of a why behind that? Is it just a lack of knowledge?
it's a combination of things, Micah. And when you're a protective relay engineer, you're concerned with proper settings and configuration of the relay itself, in terms of the differential settings, in terms of the overcurrent settings, in terms of over and under voltage or volts per hertz. You're worried about all these protective elements, but through faults create damage in the transformers that is more of a focus for your asset managers. And there just seems to be a lack of communication in terms of why these things should be enabled. So when you go out in the field and you do your maintenance testing on a transformer, you don't really pay attention to the protective relay system. It's two different disciplines.
Right.
Now, when we talk about contract service testers, your NETA people and whatnot, they're kind of like a jack of all trades. Not only do they know how to test relays, but they know how to test transformers. But they're not investigating whether or not those relay systems are properly set unless they were, part of an engineering team that developed the settings.
Well, and I was going to say that might be an encumbrance there, is because you have relay setting engineers that are doing that more so on the other side, Bice, in the
Yes.
field. So is that one of the encumbrances, kind of?
Oh yeah.
Gotcha.
So, every time I talk about transformers and I talk about maintenance testing, I always bring in an element of the protective relay system as well. And historically, sometimes those groups never get together. It was funny. I was at Power Test a year ago, and one of our customers who works in a service industry came up to me and said that he was responsible for testing and commissioning a relay that was on a generator step up at a nuclear facility. Well, he got a call saying that the transformer had tripped offline. The differential element tripped it offline. So, he gets in his car and he drives out to the facility. And by that time, the maintenance supervisor already has his crew out there, and they're putting up scaffolding and they're disconnecting the mains to the transformer, and they're getting ready to do their power factor test and TTR, winding resistance, excitation, the whole battery test to find out what happened internally to the transformer that caused that nuisance trip. Well, when the relay guy gets there, he says, "Hey, did you guys happen to look at the fault recorder, the oscillography of the fault itself?" And he was like brushing him off, "No, go away, Sonny. We got work to do. We got to find out what's wrong with this transformer." Well, as it turns out, there was nothing wrong with the transformer. The relay nuisance tripped.
Wow.
And by looking at the fault recorder, they could see there was no differential relay whatsoever. And unfortunately, at times, protective relays do misoperate or fail internally, and create a situation of taking a piece of equipment offline. So, moral of the story is if they had waited for the protection guy to give a thorough analysis of what may have happened, they could have saved themselves a lot of trouble and gotten that transformer back online a lot quicker.
And scaffolding to put up is not cheap. I know that from experience.
Oh, no, and disconnecting all the yeah. I mean, that's a lot of work, especially when you're talking about a nuclear facility, and nobody wants to take a nuclear reactor offline.
Definitely not. Most definitely not. Now, with regards to the throughput, so you mentioned it'll throw it offline. Does it have an automatic reset function as well within the protective relay?
Well, yeah, and that's a really good question. So what a through fault monitor does is that it looks at the through faults and it actually records that information. Now, in transformers, typically when they came from the factory, have what they call thermal limits, okay, in terms of how much load you can put on the transformer and what its thermal rating is. And that, of course, has to do with the temperature, the operating temperature of the transformer. What they never really had in the early days was the mechanical limits associated with a through fault. And so IEEE came and they developed certain criteria for how much a through fault that a transformer could withstand. And a lot of that, how much it can withstand, really has to do, again, with the design of the transformer. Because we know that through faults are typically more damaging to a core form transformer rather than a shell form. And that's because the shell form has multiple current paths to kind of absorb, that current, that current inrush and that current flowing through the transformer at very high levels. That doesn't mean that a shell form can't be damaged by a through fault. Any really very high through fault can damage just about anything. But they're depending on the classification of the transformer, and classification has to equates to the size of the transformer,
right,
or how big it is. So there's basically four categories of class 1, 2, 3, and 4 transformers, and it's all related to the MVA rating. So that helps also determine when we're going to alarm based on a through fault. So basically, there's three things you have to look at. Number one is what the magnitude of that through fault is. If it's just a very small through fault, maybe in a distribution circuit you had momentarily had a branch fall on a power line. Okay, that creates a fault, and that will create a through fault for the transformer that's feeding that line. Okay, so it's not something that you want to take the transformer offline of, because it's not going to damage anything. Okay, it's just a momentary thing. So the duration, how long that lasts, that through fault lasts, the magnitude of that through fault, and how many occurrences you've had. And that's what the relay is going to capture, all this information. Okay, so the recorded values can actually assist a substation crew in prioritizing transformer maintenance and testing. And that's important. If you have a through fault monitor on your transformer, and over a period of time between maintenance periods, you've seen a significant number of through faults, then you want to test for mechanical damage on that transformer. So it is a cumulative record. Now, if the through fault is high enough and it exceeds the mechanical limits of the transformer, it's going to give you an alarm and say, look, you've had a really high through fault. Maybe you had a downstream situation where you had breaker failure, and that through fault hung around a lot longer than it should have because the breaker didn't open when you had the fault. Okay, that's another situation that can, cause your through fault alarm to go off. So basically, if you have a through fault, and let's say a Schweitzer relay or another digital relay picks that up, it's gonna date and timestamp that through fault. It's going to record how much current actually flowed through on each of the three phases and what the duration was in terms of time. So let's say you have one that occurred on, let's say February 14th, and at 12:30 at night, and the duration was 5 seconds, and here's the highest amount of current that went through. Then you had another one 4 days later, and that one was 30 seconds long, a much higher duration. So you have all this information to help you determine what type of testing you should do, or whether you feel like it's significant enough to possibly cause damage, and then test to make sure that there's no damage that's occurred.
Makes sense. And then for like the protection, so let's say, do you have the ability to go in and change your settings in that protective relay a little bit to where it will it'll trip the transformer offline, or can you set those standards for posterity of the transformer itself? So if you see it and you want to make sure you're preserving that.
Well, there are protective elements in the transformer relay to actually take the transformer down if you have a significant fault outside the protective zone of the differential, in things like instantaneous overcurrent relays and things as such. So yes, but in most cases, a through fault would not trip the transformer.
Okay, gotcha.
And that's kind of the big concern, because you don't know. If you don't have a through fault monitor on there,
You just won't know.
No.
Absolutely.
It's hit or miss.
Now you mentioned breakers and like a branch down, and you have all the various concerns. Obviously, that's why it's very important to keep the trees trimmed back, right? But what are some of the other
good? That's a very good point, and I'm glad you brought that up, because part of the information that you get from looking at through fault records is, especially in distribution, do we need tree trimming maintenance going on because we've seen so many through faults, over a given period of time? Well, let's dispatch our crew out there and see where this is happening and take some proactive, approach to fixing it,
Definitely makes sense from that aspect of it. And then like what length of distribution is it vary between? So like let's say you have this protective, relay that's monitoring for through faults and all that. And let's say it's a line. Is there usually a typical associated range, 5, 10 miles, 20 miles down, or how often are these spaced out with regards to real-time monitoring?
Yeah, and that's a good point because the location and the topology of the system that the transformer is feeding, has a lot to do with the significance of the closer in the fault is to the transformer, the higher in magnitude that's probably going to be. So if it's further down the line, a lot of that fault current is dispersed by the time it flows through the transformer.
due to the
Um,
various
and,
losses,
and a
transmission
lot of that, I
losses, and
mean,
things?
it's not just in distribution, but you certainly have the possibility of through faults on transmission lines, high voltage, and EHV systems as well. And that's why the settings are slightly different. Now, the settings have had two categories when you set the through fault capability for transformers. One is the time in terms of magnitude, and the other is times the base rating current level of the transformer. So we know that a transformer can withstand, let's say, 10 times the base rating, for 10 seconds. Well, if it goes further than 10 seconds and that times base rating current is higher than that, well, that's going to trigger an alarm.
Gotcha.
Okay, and that's going to trigger a record. So we know, we use these time versus magnitude curves to kind of determine when we're going to capture the information.
Makes sense. Definitely makes sense. And now with throughputs, are transformers the only piece of or component that will actually experience through faults? Will it affect other components within a distribution or station? Or
Yeah, it can. No question about it. You have, capacitor banks, and you have, you know, various other pieces of equipment. A voltage regulator, kind of the same thing. Voltage regulator is usually outside the substation and regulates the power to either decrease or increase voltage as the loads tend to get higher or get lower. But certainly not the significant damage that a transformer can experience from a through fault itself.
that makes sense. And then with the transformer, so obviously the throughput's affecting that transformer and degrading it. Is there like a standard, like we talked about it being valuable from the maintenance perspective and knowing when you want to do it. So is there a frequency that triggers the technician that's like, hey, I need to go check this out now? Is it, as far as parameters go, like the frequency with which you're getting the through faults?
Oh, sure. Well, basically, it's a good information to have if you have routine maintenance testing that's being done on a periodic schedule. Let's say once a year. Okay. So, when you have your routine set of tests that you do diagnostic, you go out and you pull your dissolved gas analysis, then you do your power factor testing, then you maybe do excitation, and then you'll do your turns ratio test, and then you do your winding resistance test, and if everything looks good, then you're very happy about that. But there's two other tests that if you have a through fault monitor and you've seen quite a frequency of through faults happening, or you've seen some that with particularly high magnitude, or if your alarm's gone off between these maintenance periods, you should do some additional testing to make sure you don't have any mechanical damage in the transformer. And here's an interesting thing. If you do not have any through faults recorded from that recording, you can skip a couple of different tests that we typically do. If you don't have a through fault monitor and you have no clue whether or not you've had through faults going through the transformer, then you should probably incorporate some of these additional tests as well.
Makes sense. And then, so on average, like how many of these relays would you say are actually implementing that throughput fault monitoring? I know we mentioned it being an issue. Is there a higher propensity for it to be set or not?
Well, the only the only information I have is people that I've talked to and asked whether or not they've had that enabled. And that's kind of a difficult survey question. All I know is what Carl referred to me at Schweitzer and saying that, boy, not many people seem to enable this. And that's really the only feedback I have with regards to how many people do and how many people don't. And that's kind of a scary thought when you think about
It
it,
really
because
is.
you can sit there with a small amount of damage and it's not going to show up in any of your common dielectric tests. until it gets to the point of no return and, creates a deformation in the core or collapsed tap winding or buckling of the winding or, any kind of displaced internal connections. And, it can eventually create a pretty bad internal fault in the transformer itself.
That makes sense. Now, with regards to, so we spoke on moisture abatement last time. The moisture component of this obviously has a pretty big impact. Does that impact the throughputs as well? With
Not
regards to
really. I
heat
mean,
and
whenever
things of
you
that nature?
have, I mean, if your insulation is getting weak, anything can cause a problem. But again, this is kind of a different category with regards to typical failures in a transformer. If you break down some of the reasons why transformers fail, number one is usually bushing failure. Number two is online tap changers, because they're the only mechanical moving part in a transformer, and they draw a lot of current and they arc, and it's a moving part. It's one of the failure points that's under a lot more stress than just the solid insulation or the windings or the internal components. So I think one of the problems is, Micah, that I think people don't pay that much attention to through faults because it's not one of the higher causes of transformer failure. It's kind of a little bit lower than the other issues on the totem pole. But I'll tell you what, when you do have mechanical failure, it's almost always catastrophic and beyond repair.
And then we also mentioned that being the case with the bushing failures as well, on that
Yeah.
instance where you get the big boom that kind of accompanies it,
Yeah.
right?
Yep. So basically, we have, in order to detect whether or not through faults have created any kind of mechanical failure, we have two different types of tests. One is the one most people are familiar with, and that's what's called sweep frequency response analysis, or SFRA. And this is all part of, if to get really in depth of how this works, what it does, and how to do it. This actually has an IEEE guide, which is C57149, and that is the IEEE guide for the application and interpretation of frequency response analysis for oiled immersed transformer. Now, the published guide was last published and released in 2012, and for the last, I'd say, 5 or 6 years, it's been going through a revision and getting updated because there's new transformer designs. And, anytime anybody in the Transformers Committee gets a new approach to running these types of tests, they want to update that guide. Well, what IEEE Transformers Committee says is that, well, when we develop a guide and we publish the guide, or we publish a standard, we're going to say that that's good for 10 years, and that's it.
Gotcha.
And
Makes
then
sense.
after
New
10
tech,
years,
right?
it's run its course, and you must get it updated. So this
Gotcha.
is one of them. I have a very good friend of mine that works for OMICRON as an applications engineer, and he's been the chairman of this committee to get this revised for a very, very long time. And he's really the guru in SFRA because it can be a fairly complex test. Now, the other test we have, and we'll get into this a bit, is what we call leakage reactance, or otherwise known as short circuit impedance. And think of this. Let's say in a transformer, you have what we call flux, right? We energize the core of the transformer, and you get all this
Magnetic flux
goes
lines
into the transformer. Well, think of this as, let's say you have a wooden trough, and in that wooden trough you have water flowing downhill, and naturally you're going to have a little of it spill out and leak out, maybe absorb into the wood. So the water that starts at the top isn't always equal to what comes at the bottom because you have normal leakage. Well, let's say somebody came to that trough and they took a big rock and they put it right in the middle. Now all of a sudden you have all this water leaking out and pouring out all over the place. Well, flux in a transformer is the same thing. And we measure the flux in terms of impedance, the overall impedance of the windings of the transformer. So if you have physical damage in the transformer itself, you're going to have more leakage flux, again, measured in terms of impedance, than you normally would. Now, so when a transformer leaves the factory, they're going to measure the impedance, the overall impedance of the transformer, and they're going to take that number and they're going to stamp it on the nameplate. So when you do a leakage reactance test, what we're going to do is we're going to go out and actually measure that impedance. And according to IEEE standards and industry standards, that measurement must be plus or minus 3% of what was stamped on at the factory.
Gotcha.
If it's higher than that, greater than 3%, then you may have a problem. Okay, now they take it one step further. That's called the three-phase equivalent. In other words, we're measuring and calculating the impedance across all three phases.
Gotcha.
Then what you'll do in a leakage reactance test is you'll measure the impedance of each phase individually, and those phases must be within 3% of each other. Okay, because if you have one that's higher and it's greater than the others by more than 3%, that tells you that particular phase of the transformer is where your problem may exist, in terms of physical damage. Now, what are the terms we use for physical damage? Well, there's a number of them. We have things like, hoop buckling, core movements, faulty core grounds, winding deformations, winding displacements, hoop buckling, broken clamp structures, shorted turns, and open windings. These are all things that will show up in either an SFRA test or in a leakage reactance test. Now, does everybody do leakage reactance, when they go out and do maintenance on a transformer? No. In fact, I can tell you this because let's say you rent a Doble M4000. Well, if you're going to do leakage reactance, you grab another piece of equipment. And I know there's a lot of M4000s that don't go out with leakage reactance capabilities. And a lot of that depends on what the testing companies or service companies' testing specification calls for.
Mm-hmm.
Now, what would call for that? Okay, now my suggestion is this. If you do not have a through fault monitor on your transformer, your maintenance testing should include leakage reactance tests. It's not a very difficult test, and it doesn't take that long to run. If you have a through fault monitor that has recorded a number of through faults, regardless of the magnitude or the duration, but let's say you've had a lot of them, then you should incorporate a leakage reactance test. If your through fault monitor hasn't recorded any through faults, and you're confident that you haven't had any based on that lack of reporting, then you can skip the leakage reactance test.
Makes sense.
Okay.
And so would that be your go-to if they don't have through fault monitoring? You need to do the leakage reactance test.
It really should be. I mean, if they have and through fault monitoring isn't just in the protective relay. Let's say you still have electromechanical differential relays and discrete electromechanical.
They're still out there.
Yeah, they are, by all means. There's a lot of companies that make discrete through fault monitors. I know it's incorporated into some of the dynamic ratings monitors, and Doble's Callisto, I think, also monitors through faults. But this is a very important process in terms of maintaining the health, and watching for the health of the transformer itself.
Now, will a through fault impact the tap changer as well? Is there any ties there to the mechanical side of it? Would that be the only mechanical component?
No, the through faults basically don't have much effect on the OLTC. That's a different mechanical failure altogether.
Okay, gotcha. I'm throwing the layman's answers out there because I'm still still trying to learn here.
Now, to take this one step further, okay, the more definitive test for mechanical failures comes in the form of sweep frequency response analysis, or SFRA, and this is the one the industry is most familiar with. Before a transformer, an SFRA is like taking a fingerprint of the windings of the transformer and the internal components of the transformer, because they all have a unique defined characteristic when they become manufactured. So in a lot of cases, what you'll find is that a customer buying a new transformer will specify to the manufacturer, look, I want you to do this SFRA test at the factory, record the response of that frequency sweep, and that will stay with the transformer throughout its life. Because when you follow up with that and you do a subsequent one, you're going to compare the two traces. And any deviation of the response of that test will indicate a possible mechanical failure. And one part of the test is all about the core movements. One's about the the internal spacers and the windings. So you get different types of information and more thorough information about any mechanical failure within the transformer that may have occurred. It's a little bit more complex to run in terms of that versus the leakage reactance test. But anytime you have a leakage reactance test that shows a suspect mechanical failure in it where the impedance is changed um, above the specification, then always recommend to follow up with an SFRA test. And it's kind of like a chest x-ray when you do SFRA. You look at the response of the frequency response, going from, when you get a chest x-ray, they go from front to back, then they go back to front, and then you turn it on your side and they go from this way and they go from that
Right.
way. SFRA is kind of the same thing. We compare the high side, A phase to C phase, B phase to A phase, and, back and forth. And we're checking, we do a series of what we call open circuit tests on the high side and a series of low voltage tests, open circuit tests on the low side, and then we'll do short circuit tests. And what's interesting about that is the response that you get, depending on where the damage is, okay, can indicate a failure that is the result of a through fault, which may look different from mechanical damage from transportation or from seismic activity. So, you get a lot better indication that through fault has possibly damaged doing an SFRA. So we know that let's say in a three-phase core form transformer, through faults are generally associated with low voltage winding in the form of radial deformation. So your diagnostic focus will be given to the low voltage open circuit test and the high voltage to low voltage short circuit responses. So if you see deformations in either of those tests, that's an indication that your mechanical issue is a result of a through fault. And this is all in the C57-149 guide that I mentioned earlier. If you want to dig into great detail on that, it's an
I'll definitely take a gander. I love this stuff. It gives you a reason to kind of nerd out on it. And now you mentioned, so this kind of piqued my interest. We're talking about the standards being good for 10 years whenever you go to these IEEE working groups and things like that. What does that process look like to update that? That's more just, I know it's kind of off topic, but I just picture it in a smoke-filled room with a bunch of guys pointing fingers at each other and all that, because obviously there's a pretty substantial time delta of 10 years,
It's the very first thing you do is you get the existing standard on schedule to be redefined or to be updated. Now that update process can take 5 years.
Wow.
So, that's a long time to get a standard updated. So they'll say, okay, they'll assign a chairman, maybe a co-chair or secretary to a working group to update that particular standard. And then twice a year when we meet overall, they'll schedule a session for that particular working group. Now, you can have people come in and join and be members of that particular working group. And, you're the SME that's going to contribute to updating and revising that standard. So they'll do it different parts at a time on the standard. Maybe they'll change the scope a little bit. Maybe they'll change certain sections of it and add more intelligence to it. And the gurus that have all this knowledge about what's new in terms of that process will give their input.
Makes
Well,
sense.
then this takes a considerable amount of time because it's very important to listen to the input that everybody has with regards to that. So we don't want to, excuse me, we don't want to keep anybody away from giving their input. So what that means is you have a tremendous amount of opinions and input, and sometimes you have to weed out any of the commercial component that
Makes
somebody
sense.
came up with a new process.
Absolutely.
But
And is there like a comment period typically associated where you take inputs from industry, techs and things like that?
Mhm.
Okay, I kind of
oh,
figured
oh,
as much.
oh yeah. And then, once you have a draft, it goes through multiple channels. You have a draft where people can review the draft and then comment on the draft, and then everybody's comment has to get reviewed from what they call the comment resolution group to say
Right.
either no, you don't have a valid comment, we're keeping it as it is, or we'll consider changing based on your recommendations. Then it has to go through various committees to get final approval, and then finally, you're done. And I said
And
again,
then you start the process over again, right?
yeah, in another 5 years.
I was going to say you've been doing it for 25 years, so I knew you'd have insights into that process there.
Yeah, it's good. But you know what it does? It forces everybody to keep an open mind and brings in as much information and intelligence as possible, be it good or bad or indifferent. It's by the time a standard gets released or revised, or there's been a tremendous amount of man hours put into that to just make it as best as you can.
Absolutely.
But getting back to leakage reactants and SFRA, one of the things that I always try and emphasize is that who's ever either setting relays for the transformer or maintenance testing on the transformer, you have to become familiar with the nameplate of that transformer. And they all look different, based on the manufacturer, based on the size, the type transformer. But that's like your heartbeat of information is that nameplate. On that nameplate, they stamp the impedance of the transformer, and that's what you compare it with, because that's the very last piece of information they get on that nameplate, because they don't know what that impedance is going to be until it's completely built and finalized and they run that test. And they all look just a little bit different for sure. But the nameplate has your voltage levels, the number of taps on your tap changer, how it's configured, the high side voltage, the low side voltage, the MVA rating, your CT ratios, all that information's on the nameplate. And whether you're doing relaying or maintenance testing, you have to understand and know this information, because it's going to affect your testing, it's going to affect your relay settings, and it's going to, guide you through the whole testing process when you go to test the transformer.
That makes total sense. And then so we're almost to 45 here, so I just want to make sure what are some of the more what are some other salient points when it comes to throughput faults? I know you're getting ready. I think you're presenting this at Power Test 25, if I'm not mistaken.
Mm-hmm. Yep.
And
Yep.
so, what are some of the other concerns that our audience should know about?
Well, I think what's important, and I will reiterate this fact, and that is, when you need to have when you need to do these tests, when it should be included in your test standard. And I'll just give you a good example, because remember we talked about the protection system and the differential relaying inside a transformer. Only takes the transformer offline if that fault has already occurred. Okay, that's
Gotcha.
one of those reactive components, not proactive. Because
Right.
if you have a differential trip, unless the relay has failed and nuisance trip, the damage is done. You're just keeping it from getting catastrophic. But I
Gotcha.
think what's important for people to understand is if you're going to do, let's say, leakage reactance test, whether you're using test equipment from Noble, from OMICRON, or from maybe Raytech or Megger, one of the other pieces of equipment that they do other tests with has the capability to incorporate that test into the testing process. So, we have to get out of the mindset that advanced testing, types of of things that you're going to do does not equate to being more difficult. Okay.
Gotcha.
And I hear this a lot of times. Oh my gosh, that's one more test you want me to run. That's going to cost money. That's going to take time. And it's really not necessarily the case. I mean, it's like an ounce of prevention worth a pound of protection. I mean, so I have a case study that I present with this particular occurrence of through faults. They had a 50 MVA transformer, two winding transformer that tripped offline with the differential relay, and they didn't have a through fault monitor on there. Well, they went out and they did their typical tests. They did a power factor test. They pulled a DGA, sent it off to the lab, but in the meantime did a power factor test. And on the low side of the windings, that wouldn't even give them a result at 10 kV. So they lowered it to 7,000 volts, and that power factor was like almost 50%, which is clearly unacceptable. I mean, that's a clear indication we got a problem right there.
Right.
Well, we know there was an issue. We don't know where it was. So then they looked at their dissolved gas analysis, and this is something you always have to have historical analysis on. You want to see your gassing levels on all types of gases historically to see if there's any elevation that looks out of the normal. Well, when they did the DGA on this particular transformer, I think the acetylene climbed from 0 historically up to 21. And that's like, oh my gosh, we got a serious problem. Well, they did a leakage reactance test, and this is why it's important in leakage reactance to do both the three-phase equivalent and the per phase. Because on the three-phase equivalent, I think the deviation was like 2.5%, which is well under the 3% limit that you should have. But when they did per phase, they saw that the B phase had failed. That was like 9 or 10%, not within that 3%,
Right.
which should be per phase. So, okay, what do we know now? Well, DGA says, yeah, we got a problem. Power factor says, yeah, we got a problem. Leakage reactance says, I got a problem on phase B.
Right.
Okay, I got a problem on phase B. So next they do an SFRA test. And that indicates that showed like a high impedance fault on the phase B on the low voltage winding. And this was, again, evidenced by the results of the low voltage open circuit and the high voltage to low voltage short circuit test to kind of give us more evidence. So now we know which phase and which winding we have a problem with. Well, when they tore that transformer apart, you should have seen it. It looked like, that particular winding looked like spaghetti.
I'll bet it did.
All the result of a mechanical failure in the form of a through fault.
Through fault. And I get that's kind of the answer to my next question. So if you find those indications where you have a full phase, it's a loss at that point. That transformer now comes offline and it has to go out for refurbishment, remanufacturing, and now you're down that line.
Well, in this case, scrap metal.
I mean, fair enough.
Yeah, but yes, I mean, in of course there are, depending on the size, type, and the amount of damage, there is some opportunity to have it refurbished. But again, through faults can happen, over a period of time, and it's always good, especially in distribution, if they're happening reoccurring, that you find the source of that through fault, take remedial action, out in the circuit. But sometimes you just can't help but have a high through fault that's going to be damaging, and it's important to understand that before you have some type of real catastrophic failure. But any type of diagnostic testing on a transformer is just not a one test tells all. You do a series of tests, and you start at one point to kind of identify, yes, I have a problem, then take it further to try and clarify exactly where that problem is. In this case, it was, yeah, we got a problem, the differential trip, there's something going on in the transformer, to, yeah, we know it's on the low side, yeah, we know it's on B phase, through the sequence of tests. Now, regardless, you're going to have to break the transformer down and and try and repair or scrap it anyway. But it's good to have all this data and this information.
And any last minute thoughts on throughput? I definitely want to ask you about where we're filming from today, which is the Omicron
Sure.
Training Center. So, and it looks like it's a heck of a little organization there. I know you and I got to talk offline a little bit beforehand, and it looks
Right.
phenomenal what I'm seeing there.
Oh, yeah.
But any last minutes on through faults before we kind of talk through the training center there?
Yeah, let me give you my last words of wisdom. Um, be diligent in defining your maintenance testing when it comes to transformers. Be very diligent. And that not only is advice for the asset owners, whether it be a utility or industrial, but it's also the responsibility of the service provider that's going to be testing to really communicate with that asset owner in terms of what should be done. Because all too often, you'll get maybe a salesperson, and not to say there's anything wrong with salesperson. I've been in sales all my life, but you have to have the relationship with that asset owner and with that customer to clearly identify what needs to be done, to help extend the life of that transformer. We talked about this with moisture a lot. Just relying on a DGA to say whether or not your oil needs processing without going to the extent of doing a dielectric frequency response. Same with mechanical failure. If you ask the right questions of your customer, do you
There you
have a
go.
through fault monitor? Has that through fault monitor been investigated? Do you not have a through fault monitor? Should we incorporate a leakage reactance test? Here's why you should, and it's not going to drive the price up, astronomically. It's just another fairly simple test to run that's going to give you this information and, be a little bit more proactive in your diagnostics.
Absolutely. And would you say that that's a lot of the servicing agent or the servicing company that a lot of that falls on their shoulders because the asset owners may not necessarily know, they're not necessarily tied in and all that. So it ought to be a part of
Well,
informing the
who's
customer.
who's writing the test spec,
Right.
right? Is it the asset owner? Well, if the asset owner is writing the test spec, why isn't he doing the testing himself?
Right.
So does it come down to being astute and knowledgeable in terms of what should be testing? Or is your sales team not concerned with anything other than getting a low bid on a spec?
Exactly.
Um, and the proof is in the pudding, and I'll tell you why. We have a classroom full of industry experts here that are in the field all the time. How many do you think knew about DFR?
I know we talked about it on our last conversation. It was very, very few. So
Same thing with leakage reactance.
right.
Why do we do leakage reactance? It's generally known that SFRA is a test for mechanical failure. I mean, pretty much anybody that's tested a transformer knows about SFRA. But if the common knowledge is that, gee, I only have to do that if I'm moving it from location A to B,
Right.
then I don't have to worry about it. Well, what about through faults?
Right.
Which
No,
is
totally makes sense.
the biggest cause of mechanical failure in a transformer. Because some of them don't move 50, 60, 70 years. They haven't,
Right. Right.
there's no seismic activity. I mean, you live out in California, that may be a different story, but that's just, my words of advice is be diligent. And understand what your protective relaying and your monitoring system is doing for you. Make sure that's enabled. Make sure your digital fault recorder is enabled. Make sure your sequence of events information, any information that you get when you've had a fault on any power system, your interrogation starts with looking at fault recorders and sequence of events recorders to try and figure out what's happening.
Makes sense. Those are going to be your initial indications that you have a problem. So if you're not looking, you're
Hey, Mike, I have a special guest here.
awesome.
I'd like to
Who
introduce.
you got?
Come on in, Darren. This is my good friend and former colleague with OMICRON, Darren. And
Hey, Darren.
Darren is the area sales manager for OMICRON here out of Houston, Texas. And he's been with the company how long, Darren?
11 years.
11 years.
11 years. So he definitely knows what's going on over there.
He does. He's a great guy. And he was part of our training session that we had over the last 2 days here at the training center here in Houston. And this was kind of a brainchild of a good friend of mine that retired last year. His name is Will Knappich. and Will was the facilities manager here when they built this building.
Oh, wow.
So in front of me, what you don't see is a beautiful classroom that holds about 65 people. And there's a glass window right here. I don't know, you can't see the glass, but behind the glass is the hands-on training center. We've got a
Very
big
cool.
transformer out here. We've got a couple of breakers. We have CTs, PTs, and, Darren, tell us a little bit about what you do in terms of training programs here at this facility.
Can we get him on screen there? I want to see
Oh,
what
yeah.
Darren looks like here. There we go. Hey, Darren.
How you doing, sir?
Great.
What we offer here at OMICRON, we offer classroom and online training. We also offer customized training for a particular asset, and we also offer webinars here. So just like Drew said, this is kind of like in a controlled environment, so you don't really have to have all the FR clothing on when you're testing in the field. So the classroom is used pretty much to kind of go through the theory portion of everything. And then from there, we can translate that and take it to the action into the lab. And we can use that and do the hands-on portion to, take that theory that we use to test a particular asset. And now we're doing a hands-on portion.
Very cool. And that's how it doesn't make sense to have the educational if you're not turning that into hands-on, or it's just going to go away like that. So definitely the way of the world and kind of how that works for sure.
Well,
And so Darren, how long has the facility been open?
Here, I've been here 11 years. I would say about 15 years
Okay.
at this location. But I was kind of one of the first people to help that he was talking about with Will Napick to get everything going, because we did all the feeds to bring the power into this building. So Will and myself. So I know kind of all the ins and outs with all the equipment here. So so we did a lot of the first setup of everything that was here in the academy.
Very, very cool. Now, how often do you guys typically run new classes coming through? Like for on-site? If it's online, you can pretty much access it anytime. Do you guys have a frequency with which you stand up classes, or is it pretty much by demand from customers?
It's a variety of both, right? So we have customized training on our website every other month, and then if you want some specialized training, we can use that time to pick particular days. It kind of goes with your team needs, right? And we can kind of fit in with our schedule to do a particular training.
Can you kind of give us a broad overview of what does a typical training session look like? What are y'all typically working through and covering? Is it sky's the limit? You cover everything, or like you mentioned, the custom trainings there, so they can kind of tailor it. But on your standard curriculum, what are some of the things that technicians can expect to learn while they go there?
For the training itself, you go through the theory. All depends on whatever the title is, right? You have the hands-on portion, right? Feedback section to, if you have any questions, right? So a lot of times you may have more questions just that you've may have read in a book, right? And so with that time we have here, it all depends on how long the course is. You're able to, ask the experts that's here, and then you can also, take it in the lab and put it to action.
Very, very cool.
So these past 2 days, we've had some great customers in. We had people from Eaton, from Schweitzer, from some service companies that are out there, and some very smart people. But the way we organized it was, I always say I have that saying: if you don't know why you're doing it, don't do it.
Don't do it.
So we take the classroom opportunity to explain. And not only the process of how to run the test and what we'll be doing once we get on the lab, but why we're doing it. What are we looking for?
Exactly. The why is very important.
What kind of results are we looking for? But, a lot of people go through training. They go out in the field and they learn how to do this test and that test and that test without really understanding why they're doing that test.
They're button pushers at that point without understanding the theory, right? So that's a bad situation.
So Darren and I and a number of people from OMICRON that are subject matter experts, teamed up to do just that over these last 2 days. And
that is
we had
awesome.
some very sharp, very, very smart, very experienced people in the class, and they all walked away learning something new and something different. Even if it's a review, it's always good to kind of, oh yeah, I remember I do that.
It's like those CTDs and continuous learning are a blessing and a curse, but you have to have it if you want to stay sharp and on top of your game, you know?
The other thing, Micah, that's important about this, and when you bring a group together, is to listen to what your participants also have to say in terms of their experience.
Mm-hmm.
And there's never been a session that I've gone through where I haven't learned something from the participants that come, whether it's a story. I mean, when I do my Why Transformers Fail out at the Protective Relay session at Washington State or Washington Institute at the Pullman, used to be in Pullman, now it's in Seattle or in Spokane. Everybody loves to come up after the class and show me pictures of this bushing that was on fire, or this transformer that blew up, or I get a lot of experience that people have had just by listening to what they have to say when they come to class.
It's like trading war stories for us old Navy salts, sitting at the VFW or something like that. So I totally get it. I imagine you probably get a pretty good trend analysis based on some of those conversations and kind of see what's spelling out there and things like that.
Yeah.
So getting that real world feedback, because as you know, you're traveling all the time. You're not the one out there typically on top of the transformers doing the thing. So any of that feedback you can get from the field seems like it would be beneficial.
But
for sure.
what's important in the industry is this whole educational process, and not only here at Omicron, but I've teamed up with people at the AVO Institute, Maker up in Dallas, a beautiful facility there. I know Darren's familiar with that. Doble's got their training facility. We left here yesterday after the training session, and the guys that were here from Eaton took me over to their training center, and I was absolutely blown away. It's just amazing. So Darren and his team could go over and see that training center. They can come here for education, and there's just this wonderful sharing of knowledge in the industry that is just
and that's one of those things that we hit on it last time. And I'm biased, like we all work in power. It could be very well the same in retail and hospitality or whatever. But just to see the amount of knowledge that's shared openly, even amongst competitors where you wouldn't think it would be the case, everybody is so willing to share their knowledge. I've only been to a couple events like Power Test and a couple other little here and there's, but just to see that level of collaboration, like I said, I don't know if it's unique to the power industry, but it is just always impressive to see. I know you came to us last time from the IEEE T&D conference. You had Prolux sitting right behind you, and having those conversations, just being able to share it across the board, and even amongst our competitors and things like that. I would go and hang out with IPS for a little bit over here, and then we go hang out at Shermco, and then everybody would come together and just share ideas and philosophies over a beverage or two, perhaps.
Look at some of the responses we got from our last session that we did on moisture. I mean, you had guys from Australia chime in and talk about
Israel and Cargill and everybody.
The guy from Cargill, and and guys that share their experiences just in a social media environment, and that's cool as well. And that's one of the things that these interviews you do, which are just fantastic, bring to the people in the industry that may not get a chance to sit through a 2-day session on training.
And just to be able to expose, or bring to light the OMICRON Training Center, like a lot of the technicians are out there, and I've been there where you work in 40, 50, 60 hours a week. That's not the last thing you want to do, but if we can break it into micro-sized chunks and perhaps make people aware of what's out there, it only benefits, and and hopefully we're having some sort of at least minuscule impact, and we're trying and doing it, and many thanks to guests like you and Darren that come on and share the knowledge, and it just goes to show you what an awesome industry power is.
You bet. Absolutely.
Well, Drew, my friend, we are up to an hour and 5 minutes, which we're doing pretty good on sticking on time. Do you have, actually, I'll ask Darren, do you have any advice, any guidance that you would like to give to people? Where can they reach out to talk? If somebody wants to schedule training and things like that with the OMICRON Academy, who's the best point of contact and things like that? And who would be best to reach out to?
First, I can just say, I would go to the website, www.omicronenergy.com, or you can call me directly. I'm the area sales manager, Darren Watson, 713-212-6128. But just on the website, you can go in and see exactly what classes we have available, and then you could, sign up online. Yes, sir.
Beautiful, beautiful. And Drew, my friend, I'm sure this won't be our last interview. You're always innovating, adapting. I know retirement is looming, so I definitely want to have you on a couple more times. He's not going anywhere.
Right.
He'll be here till he's 100.
That's proposed.
Proposed retirement.
You never know.
I told you earlier, I tried it once and it didn't stick, man. So you may very well end up in my boots and work till you're 100.
Disaster in the stock market, I may be working a lot longer.
Fair enough. Yeah, that one definitely didn't help the bottom line by any stretch of the imagination. So that one got my chest palpitations up a little bit.
Right.
But no, as always, it was fantastic chatting with you, Darren. Many thanks for hopping on and giving us a little insight there. And we'll try to get something new. Just come up with the next topic, and you're always welcome. And I'll even afford that opportunity to you, Darren. We're always looking. We now have an official podcast. It's Spotify certified. And so we've kind of delved into that. I must be a glutton for punishment. And now I've got to always be finding those guests to fill those spots. So if you have anything you want to do, please feel free to reach out. We can get you on to have these conversations and share some more knowledge with the industry. I think it's a small part to play, but helping people with awareness and knowledge and things like that is very important to me. And I know it is for Drew and the team at OMICRON as well. So anytime, feel free to reach out. Drew, any last minute parting thoughts?
Absolutely. Okay. If you're a company looking for employees or you're an employee looking for a new career, give this guy a call.
I appreciate it, my friend. I appreciate it. And I always say I'm running around like a one-legged man in a butt-kicking contest over here. It has definitely been fortuitous for us from that aspect, and I definitely appreciate the shout-out. And we're just doing our small part to help people out. If we get a little money on the side, that doesn't hurt. Like I said, we're retired once, so we're working on getting into a new airplane. That's about it right now. So I sold my original one to start the company. Now I'm missing flying, and I got to get back up in the air. So that's the goal in life. But I greatly appreciate it. And likewise, if you guys are looking for equipment and just advice, Intellerant all the way. I know we plugged a little bit on the last one, but that's important as well. Know where you can go to get your test equipment and talk to folks. They're very, very knowledgeable. As you know, Drew's a 25-year IEEE senior member on relays and transformers. Pick these guys' brains for knowledge. Get those best practices out there. And we hit on many of those over in this conversation today, highlighting that stuff. Utilize your network resources. And that's my little final 2 cents. Well, my friend, another great conversation. I'm sure we're going to get tons of great response from this one as well. And until next time, folks, Mike out.